Please go ahead. Am I audible, right?
Yes, you're audible.
Okay, what is this? This is, for instance, this program gets executed, and somewhere in the memory, this variable, which is an integer, which has been named A, holds a value 10, right? What do you think is the lifetime of this storage? Till the execution of the program, till the program is finished, it's all gone. Agreed? Or, for instance, if I restart my machine, everything, what's happening here, I'm not writing this into a file, right, which is there forever till I delete it intentionally or unintentionally. I'm writing it into an imaginary, temporary location inside my main memory, inside my RAM, and the lifetime of this variable is till the lifetime of that particular program. Or if I restart my PC, everything in the RAM basically gets flushed out, right? Now, what basically happens is that we need to allocate, we definitely do need to allocate memory whenever it's dynamically allocated. For instance, if we talk about normal computing, there is a staunch difference between a stack and a heap. We'll talk about that later. But like for now, buffer is anything, any storage location which is temporary, which is not fixed, which is not tangible, right? It's not stored on a particular sector in the hard disk, but it entirely resides in the memory, right? So even with today's most advanced methods of defeating piracy, it is still relatively easy to crack almost any program. We get across a lot of cracked applications, right? Cracked applications, how do we crack them, right? We use debuggers and what do you call that, assemblers, in order to look into the code of that application and then crack them. So in this particular small session, I'll try that we'll first of all understand the theoretical aspects of buffer overflow, and then we'll crack a simple application, crack an application by launching a buffer overflow attack, right? And at the end of this, I'll share that application computer application can easily be disassembled or debugged in the disassemblers or debuggers which are readily available, right? And using those disassemblers and debuggers, you can easily compromise a particular application through launching any attack of your own choosing. Or, in other words, launching any attack which the application is vulnerable for. For instance, the particular application I'll be sharing will be vulnerable for the buffer overflow attack, right? I'm getting some notifications like some beeps. So it is something I have to do, Ma'am Rabia, or like you taking care of that?
It's clear from our side.
Okay. So buffer overflows are a product of poorly constructed software programs, right? Very poorly constructed software programs. For instance, just for the example of it, for instance, I say int a is equal to 10, character b is equal to this. Sorry. I can write it this way, right? And I for instance, I take this array and I copy. Now it is an array of size 5. How many bytes can I copy here in this array? Anyone? Technically, 5? I'm asking. 5, right? Technically 5, but you can actually store 8, because like in computers, the memory management is basically according to, well, what if, for instance, I write here that Pakistan and Saudi Arabia are Brothers, I can do that. Why? Because this particular function is insecure. Agreed? So it's insecure. Why? It does not check the size of the destination, which is array A, before copying or pasting the content into it, right? It's like pouring a liter of water into a 250 ml bottle. What will happen? It'll overflow, right? Similarly, it's exactly like this. Assume this character array A happens to be a 250 ml water bottle, and water you're pouring is 10 liters of water. What will happen? It'll overflow. When it'll overflow, it is going to contaminate its surroundings. What are the surroundings? These are the surroundings. A, B, right? So their values will correspondingly change, right? So since we can abruptly or accidentally change these values, we'll see a particular scenario where we might intentionally change these values in order to take the control flow of the program to a particular point of our own choosing, right? So we'll see that in a moment. Now, these programs which are vulnerable to buffer overflows, they have multiple deficiencies such as stack overflows and heap corruption and format strings and race conditions otherwise as well. But like at this particular point in time, we'll restrict ourselves to stack overflows. Now, there's a difference between a stack and heap. Like, for instance, stack is pretty ordered, heap is not ordered. And one main difference is that the static allocation of data, like this is static allocation of data, int A is equal to 10 and B is equal to X or whatever. This is static allocation. We are statically allocating. And in programming, we talk about some dynamic allocation of data where we can basically dynamically allocate. And in C++, we use these new and delete parameters, right? For new is for statically allocating data, and delete is finally deleting that as well. And old C view has these malloc functions, memory allocation, and probably some deallocation function as well. Right now, the basic one more difference between heap and stack is that in stack, you're not supposed to clear everything you've initialized. In heap, you have to. Or in other words, the memory management in the case of stack is taken care of by the compiler itself. In the case of heap, it's not the responsibility of the compiler, but the program author. For instance, assume the same program, int A is equal to 10. For instance, if I execute this particular program, then the value of 10 will be stored in A. I am assigning the variable A, which will be some register, a value of 10. Am I going to free that up as well? No, I'm not going to free that up. Why? Because as I said, memory management is the responsibility of the stack. We talk about heap, for instance, I talked about these two variables, new, which is supposed to allocate the memory, and delete, which is supposed to deallocate the memory, right? So since memory management in the case of heap is not taken care of by the compiler, so the program author or the programmer has to first allocate the memory and deallocate the memory. So heap is way more tricky as compared to stack. Buffer overflows can be as small as one misplaced character in a million-line program, or as complex, so that the entire code, which basically will be, compromised. It can be huge. It depends upon the amount of payload we have the liberty of adding into the particular program. So for this particular purpose, in this example, we'll be needing one debugger or disassembler. For instance, you have two very famous disassemblers or debuggers. One is the IDA Pro, and the other one is the All the Debug. IDA Pro is pretty good as well. So is All the Debug, since I've been using All the Debug since my teenage. So I'll go with All the Debug, right? But before that, for those of you who are still sort of confused about that, stacks are an abstract data type. We are specifically talking about an abstraction here. Stack and heap, they are not tangible. They're conceptualized abstraction, right? Stack basically is a data type that is last in, first out, right? So it's like a stack of, unlike the queue, which is first in, first out, the stack is like, just assume the, what do you call that? The stack of plates, being placed by a waiter. So the last one is first out, or the first one is last out, you can basically drag somewhere from the middle or somewhere from the bottom. So stacks basically operate on the principle of LIFO or FILO, right? So stacks are implementing using processor internals designed to facilitate the use. Like we have basically two very distinct, what do you call them, registers in with respect to stacks. One is the ESP, we'll talk about that, the stack pointer, and the other one is the EBP, which is called the base pointer. And when something gets pushed into the stack, there's a push operation, and when there's something getting out of the stack, it's a pop operation. And if, for instance, the initial state of the stack is mentioned here in the leftmost figure, it's A, B, and C. Now, something has to be pushed into a particular stack, and that is D. So we say push D, and D is pushed onto the stack. And as you can see, first in, last out, or last in, first out. So D was the last one to be placed in the center figure. So it will be the first one to be taken out. Similarly, A has to be the last value to be taken out. Besides, it was the first value, right? Now I take you to another example of how this works. For instance, I have a main program, right? That means the main program, for instance, takes two, or I'll just do it here. Like for instance, there's this main program. It takes int a is equal to 10 and b is equal to 5, right? And it calls for these functions, sum a comma b, right? And it calls for another function that is multiply a comma b, right? For instance, now these are two separate functions, right? Now, for instance, I write the implementation of these functions in x, int y. You can take any names here, right? And what you do is that you take another variable. For instance, you take int j is equal to 0, right? J is equal to x plus y, right? And what we do is that we again repeat this particular and write the implementation of the multiply function. We take int k is equal to 0 and k is equal to x plus y. Now, let me narrate it to you. It's a very, very simple program. In the main program, it's taking two variables, a and b, storing the values. Then it's calling a sum function that's supposed to add both of them, and a multiply function, which is supposed to multiply both of them. Now, if you see the sum function, there is a variable being stored here, being initialized here. That's j, right? Now, this j is basically specific to the sum function. The multiply function does not know about it. The main function does not know about it. Agreed? And whenever you execute such a particular function, can anyone tell me what would be the error in this case? Without executing, what would be the error in this particular program? Are you people with me, right? Okay. Okay, sure. So I'll tell. Now, the compiler error, without even compiling it, I'll tell you, and you can take my word for that, would be that unreferenced local variable. For instance, if I do j here, sorry, in this case, it will say unreferenced local variable j. Why? Because the multiply function does not know about j. It's only the sum function that knows about j. Or in other words, what's basically happening is that the multiply function has a separate stack, the sum function has a separate stack, right? So what goes into the sum function You have j here. The multiply function does not know what's j. Why? Because it is not in the stack of the multiply function. If you want to have it in the stack of the multiply function, you are left with only two options. Option number one is to declare it here again, or make it a global variable, because when we talk about something as a global variable, basically it becomes accessible to all the stacks down under, right? Now, again, coming back to this particular program, first of all, we talk about the instruction pointer. This is an extremely important register, and we'll have to keep a track of it while talking about the buffer overflow attacks through disassembling of the
Your
executables.
screen.
Now, what happens is, okay, it's not visible.
No, sir.
Now,
Yes, it's visible.
okay. Now, the one of the most important registers, I said, is the instruction pointer. Instruction pointer basically contains the memory address of the next instruction to be executed, right? I repeat, the memory address of the next instruction to be executed. It's like a van which runs from route A to B, and it exactly knows where it's going. For instance, if I have to go from Pakistan, I've come from Pakistan to Saudi Arabia, so I'll know, look, I'll go to the airport, then I'll go to Karachi, then I'll land in Jeddah, or probably come to Riyadh. So I exactly know what next hop I'm going to. So the instruction pointer basically exactly knows the memory address of the next instruction to be executed. For instance, in this program, the program starts with main, right? I'm sharing my screen all the time, so whenever you think it's not available, so just let me know, please. Okay, so the program starts from the main, right? The very first statement that it gets executed is int a is equal to 10. Assign 10 to some variable a. Now, at this particular point, the instruction pointer, for instance, at line number 17, the instruction pointer is pointing to line number 18. When line number 18, which is b is equal to 5, is getting executed, the instruction pointer is pointing at line number 19. But there's a problem. The problem is that when line number 19 gets executed, it's not just one line, it is a full-fledged function underneath it, and instruction which needs to be executed as well. I'm talking about line 3 till line 7. So in order to execute the entire sum function, we need the instruction pointer there. So how to keep track of the instruction pointer, which is initially pointing at line number 20? When sum a comma b, line number 19, is getting executed, the instruction pointer points at mul a comma b. But when it goes inside the sum function, we need instruction pointer here, but at the same time, we need to keep a track of this particular value as well. So it means that when the stacks are basically formed, what happens is that the actual instruction pointer is saved here, and we call that the return address. The address the program is supposed to return to after the execution of the entire stack. So what happens here? At the sum function, if for instance, this is the stack of the sum function. So the instruction pointer, which points at line number 20, is saved here as return address, and the corresponding values of the stack are pushed, so that when it is entirely executed, it returns to the mul function, which is line number 20. So that is how the instruction pointer works around. Back to the slides. So if an attacker is able to modify the contents to point the code in memory that he controls, he can control the process's behavior as well. This means that I can take the instruction pointer to a point of my own choosing, right? For instance, suppose I have two more functions here. Suppose that is authenticate. That's a function, assume. Now what would happen is that when the sums function gets executed, its instruction pointer, which is pointing now at line number 28, authenticate, right, is saved in the sums stack as a return address. I can corrupt that return address so that I can bypass the authenticate function, right? That's what I'll do in some time, right? I'm just making grounds for that. Two more registers before we move on. One is the stack pointer and one is the base pointer. Stack pointer points at the top of the stack and base pointer always points at the base of the stack, right? And from the very look of it, we can easily say that since the top of the stack is always moving, right? Because we keep on pushing and we keep on popping, so the top of the stack keeps on moving. But the base of the stack remains the same, right? It's at the ground level, right? And since the top of the stack keeps on moving, we can, that is the reason we actually have a base pointer, to have a reference, right? For instance, this one. Now, since I've said that it is a pure abstraction here, please don't get confused. The stacks are growing, but downwards. You can invert it and have a look at that, because we generally are used to see stack growing in an upward direction. Here, the stacks are growing in the downwards direction, and we don't mind that at all. Now, what happens is that address number value A is stored at, in the leftmost figure, at some memory address, which is FC, the last two, in the hexa. The next is B, the next is C. And all of them, if you see that the bottom of the stack is at a higher memory address, right? FC is at a higher memory address, F8 is at a lower memory address, and then comes F4. For instance, if D gets stored as in the middle figure, the memory address has been changed to F0. It is decreasing. With increment in the top of the stack, the memory address decreases. And now the stack pointer, as you can see, is pointing at D. When you pop D, it again points at C, right? So that is the function of the stack pointer and the base pointer. When the stack is empty, in the very start, the stack is supposed to be empty. When the stack is empty, both pointers point at the bottom of the stack, right? Since the stack is empty, the base pointer is otherwise pointing at the bottom of the stack. The stack pointer is also pointing at the bottom of the stack because the stack is empty, and it'll definitely grow and move upwards once the values are pushed into the stack. So this is what do you call that? Further more deliberation into the how a stack looks like. You have the arguments which are passed at the bottom of the stack, then you have the return address, then you have the old value of the EPP, and then you have the local variables, right? For instance, here, as you can see in this particular program, first of all, these are the arguments which are basically being passed into the sum function. So they'll get stored at the bottom of the stack. Then comes the return address, then comes the old value of the EPP, and then comes J. What is J? It is a local variable local to the sum function, right? So this is how it basically works. Or in other words, you have the, again, it's downwards. You have the previous frame, you have the parameters, you have the return address, you have the previous frame address, and the local variables. For instance, what do you think would be this stack for this function? What will come at the down? Or what will be the first value pushed onto the stack for foo? The parameters to the function, which are 5 and 4. Because the main function passes parameters 4 and 5 to the foo function. So these, first of all, 5 gets fired onto the stack, then is 4. Then the saved instruction pointer. Saved instruction pointer, in other words, is the return address. Then the previous value of the base pointer. And then comes a local variable, which happens to be 3. Right? So this is the stack for the function. Now we talk about some complex applications. Like for instance, I have an application here. I open this application and it asks for a password, right? This application is asking for a password. I don't know the password of this application, right? So I have to analyze this application in order to see what can I do to bypass this, right? For that particular purpose, I have this OLE debug, which I've already mentioned. This is a debugger which I'll be using in order to bypass this. Is my screen still visible?
Yes, it's visible.
Okay. Here you can see, it has just started push EBP and move EBP, comma ESP, and otherwise as well. What move EBP, comma ESP means? Both are basically pointing at the same thing, right? They're pointing at the same memory location. It means the stack is empty. So it'll always take you to the very start of the function. Now, I will have to search for all reference text strings, and I'll repeat it for you. I'll again do it again. Now, since I exactly want to go to the point of my own choosing, right? In order to study, in order to see what's happening in the program. And remember, I don't have the code of this program. I'm just analyzing it in a debugger, and then I'll try to figure out that whether I can actually bypass it or not. So what I'll do is that I'll search for all reference text strings and see if there is something useful here or not, right? So I say that, okay, there is something useful here, password 45899, and the default password. So what I do is that and it exactly takes me to the particular address. So it says that, okay, setting default password and reg set value and reg create key and reg query value and all that stuff. Now, I'll drive through this particular application in a way that those of you who have no idea of assembly language or who have never worked in disassemblers and debuggers are still able to understand that, right? So what we do is that we rather try to build a story, and then we'll see that, like, okay, this thing actually works. So what's happening? You just forget about the left compartment of this figure and what this tool is portraying, and just focus on what's happening here. It says a message box setting default password, right? And the reason it gives is that I'll show you. Sorry, if you go to the registry, and let me first, I should have done that before that, but like nevertheless. Okay, so what I do is I just delete this. Okay. Now what I do is that I run this application. You see, first of all, it's saying setting default password, and that is why it has taken me here. It says setting default password, and it says that in a message box, right? I said, okay, you can set the default password, and it is set one. Now what's happening is that this shows me that reg set value. What is reg set value? Reg set value is, it is a function in C++, which what it does is that it sets a value for a registry, set data for the default value of a specified registry key. It is a function. Moreover, reg create key, it creates a key, close key, query key in order to query the particular value. Now, what basically I can assume, the story I'm building it, is that it might be setting the value of the password, which happens to be 45899, very clearly written here, in the registry, right? What particular registry key? It is even mentioning that software/neat password in which hive, H key local machine. And I go there in order to see, I guess we can refresh that, or We can do that again, right? See, neat password. It says 45899. So what I do is the lazy guy's approach. I close everything. I open this file again, and I say, is it 45899? But the OK button is still disabled. It's not enabled, right? So it means that 45899 is not the password. It's basically the hash of the password, and we're not going into cracking the hash. Cracking is not a good word in finding the hash collision and stuff. So because it's not a crypto stuff, so we'll further investigate the application by opening it in the debugger again. So now what we've ascertained is that the password stored in the registry is not the actual password of the file, but something different, rather the hash of it. So we go again to find the all reference text strings in order to go to this particular point, which is default password, right? And I'm just scrolling. For instance, I don't know anything about assembly, but the story I'm building it is that it is storing a particular value in the registry key, which at the moment is of no use. I'm just scrolling, like for instance, assume I'm an A-level student, right? It is taking string length. It is doing string copy. It means that these particular functions are being used probably for the passwords. When I do string compare, my doubt is sort of validated, right? What it might have been doing is that it's taking the value of the password from the user, right? Copying it to the destination and then comparing it, right? Comparing it with the actual password or whatever that is, right? And then validating the user in order to see whether it's true or not. And just on the sidelines, I'll run this again here. Suppose I enter hello here. Hello. You see what's happened? It has taken the hash with whatever hashing algorithm we're not interested in at the moment, taken the hash of hello, that was 34184, and compared it with 45899, which is the hash of the actual passwords already stored in the registry. And since it's not coming out to be true, the comparison has failed. It hasn't granted me the access, and the OK button is still disabled, right? What do I do now? It reminds me of a quote by Bill Gates that, it's a bit funny though, that I prefer giving the most challenging task to the laziest people because they already, they find a very easy answer to that. So for instance, if I'm lazy enough, what I'll do is the smartest answer to the solution is that I'll go to the registry and change 45899 with 34184 so that whenever I write hello, its hash becomes 34184 and this comparison is okayed and the OK button is enabled. But I'm not interested in that because we're talking about buffer overflows, right? So better close it. Okay. But like most importantly, the thing I'm rather interested in is that what basically happens when the comparison here is successful. We'll have to go. Please do acknowledge that I haven't jumped into assembly even to a single bit, right? So what happens here is that we first of all see what is the string compare function, right, in C. Return values, we're interested. It returns 0 if both strings are equal, right? And non-zero values in the case they are not equal. So what happens here, that we are interested to see what happens after the comparison. It compares here, and in this very statement, J and Z, my apologies, the only explanation of assembly coming here, J and Z means jump, if not 0, right, to a particular memory location. If so, then it basically jumps to that memory location. But if it is 0, it means the comparison is successful. It jumps to this memory location. It says call this address 402360. So we are at the moment at 4024BB. We go up 402360 in order to see that when the comparison becomes successful, what's happening at 402360 memory address, which it's taking us to. So we move up and see what happens at 402360. This is what happens at 402360 memory address, and you can see enable window here. It means that here, I repeat, when the comparison becomes successful, right, it takes us to the function which is responsible for enabling the window, basically enabling the OK button, right? So we now are supposed to take the program of our code, to take the control of our code to the enable window function, right? And for that, we need to see whether the application is vulnerable to buffer overflow or not. I open it again. What I do is I haphazardly start entering the characters. It stops. I've stopped, right? And it disappeared. It has crashed. It has crashed. Why has it crashed? I'll tell you why has it crashed. But before that, we exactly need to know that after how many characters I enter, the application crashes, and I keep on entering them. And I'll have to, since you can't see that, you have to trust me with that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. It's all safe. It's not crashing. And I'm entering random characters, right? 21, all good. 22, so far so good. 23, it has crashed. It means that the password array crashes after 23 characters. This takes me to certain conclusions, and I go back to my slides for that. That's the same thing I've already explained, right? When the program exits a function, the CPU jumps to the point called the return address, where the program would resume after returning from the very function. The password verification function in this program copies the text that is typed in the password edit box to a local buffer that is just 20 characters in size, right? But when more than 20 characters are entered, it overwrites the return address. Now I'll sort of make an illustration of that. Assume that this is what's happening in this program. This is the stack of the program. This is the return address. Agreed. This is whatever it is, some local variables or whatever. And this is that password array, right? When I enter 20 characters, suppose let's say this is X, this is X, Y, and Z. When I enter 20 characters in the password, 20 random characters, it comes till here. See? But it doesn't crash. When I enter 3 more characters, it crashes because those 3 characters, basically I was entering H all the time, right? So because when H gets converted into this hex format, it does not make anything. For instance, H basically makes 0538 C0, this memory address, assume it gets translated into this memory address. This memory address does not exist in the application under examination, right? It is not existent here. Because here we're dealing with 040236Cs and all that stuff. So whenever I add random characters here, it gets translated into something. It does, it always does. But this thing does not exist. When this thing does not exist, the compiler and the operating system fail to take the control of the application there, and it crashes. And that is the reason the application has crashed. It means that I can actually take the control of the application to a point of my choosing. The point of my choosing is this. After successful comparison, it takes me to a point of enable window, and that is the point of my choosing, right? It means that I can add random 20 characters, whatever, but the last 3 characters have to be chosen carefully so that whenever they convert to 402360, or for that matter 402358, because these are knobs. Knobs means no operation, so it's ultimately going to come down to this particular point, right? So what I'll do is that I will see that around. If we can override the return address, we can make the program jump to any area of the code or memory that we like. And in the assembly, it is evident that after successful password verification, the code jumps to the enable window area at 402360, which is this. And if I convert 402360 or 402358 for that matter, because these are knobs, we don't mind knobs at all, it's otherwise going to come down without performing any operation. Now, if we convert 40235A, which is in hex, to ASCII, it becomes alpha at the rate capital Z. And due to that little endian, big endian thing, if I, no matter what my initial 20 characters are, if the last 3 characters are this capital Z hash at the rate of, it'll take the return address to that particular point, and my function will get enable window will get enabled, and I'll be able to do it, right? I'm adding, trust me, random 20 characters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And I do capital Z hash at the rate. Capital Z hash at the rate. And you can see that the OK button is enabled. Why? Because now in this case, we have, with the 20 characters, we came till here and we wrote Z hash at the rate here, so that it has taken us to the enable window function, which happens to be the point of our own choosing. And we've compromised the application without knowing its code using the buffer overflow attacks. So we've overflown the buffer. And you want to know the only reason why this buffer has been overflown? The sole reason for the overflow of this buffer was the use of insecure function. Which insecure function? This insecure function, string copy. If you go back to the browser and see what string copy does, sorry, this is string compare. String copy function copies the string pointed to by the source in the destination, and it does not check the size, right? It just copies from the source into the destination, and the secure version for that is strn's copy, right? Now, what's the difference between both is, you see, destination, source, and the size, right? That only copy n bytes from the source onto the destination because the destination is of n bytes. For instance, if I go here and for instance, I write character A5, for instance. Now, if I write strncpy A, comma, Pakistan and KSA are best friends, for instance, which we are, so it'll only copy, sorry, and then the size of A, right? So the third parameter. So what it'll do, it'll only copy this PAKIS into A, right? Why? Because it'll first of all see what is the size of A, how much it can accommodate, and that basically gets rid of the vulnerability associated with the use of insecure functions, right? So the point to ponder here is that you have to use secure functions like strn copy, insecure functions, as I started my presentation with insecure coding practices, because developers basically not well versed with the cybersecurity code aspects of it, or otherwise the security aspects of it, or code leaks and otherwise as well. So that is what happens. Moreover, one more thing is that if you're compiling something, make sure it is in the release mode. You see, you have different modes here. You have a debug mode and you have the release mode in the compiler. So make sure whatever you're compiling is in the release mode, because applications which are compiled in the release mode, they offer less information to the disassemblers and the debuggers. Employ compression and coding and encryption, because if the file is compressed or encoded or encrypted, then the disassemblers and the compilers fail there. And then we move towards the dynamic analysis, which is yet another subject. You have to sanitize your code, use lesser reference text strings, because a novice analyzer like me, he has made use of the text strings in order to reach the point of interest and use safer functions, which is extremely important, right? Yeah, string copy and strn copy in comparison and C level functions, they're rather too basic to handle, but we have to make use of secure functions in Java and Python and otherwise as well, because that is which is most widely used these days, and above all, secure coding. And for the application crackers, for instance, if you want to have a career in, for instance, malware analysis or something related to cracking applications or reverse engineering applications, then you have to, first of all, polish the computer architecture skills in order to see what's happening in the memory, what's happening in RAM, what are the registers, what is the cache, and so on. And last but not the least, you have to have a love-hate relationship with the assembly language, because that is extremely vital to do. And coding basically helps cracking. It's something which I personally believe that if you aren't good at coding, and if you are not a programmer on your own, then it'll be very difficult for you to even crack different programming codes as well. So that is it from my side, Dr. Rabia. I hope I've been able to convey at least a bit. So it's sort of on to you now. If anyone has any questions, I'd love to handle them and answer them.
Thank you very much, Mr. Walid, for an interesting workshop. If anyone has any question, I'm sure Mr. Walid would be pleased to answer them.
Assalamu alaikum. I'm Misbah. I'm from the Law College. I don't have a specific question, so I will let all the people from the IT side, if they have any questions, then I will have a little comment at the end. That's all.
Sure. Walaikum salam. See anyone from the IT stuff, if you have any questions and stuff.
Okay,
Okay, I
I
guess,
think, yes.
Misbah, you can share your comments, please.
Okay. Number one, I took away my takeaways as a law person because I worked in the cybercrime area with the Islamabad police for some 1 year.
Mm-hmm.
So that was very interesting experience for me. And I
Mm-hmm.
work on digital evidence collection. This is an area of my interest and my research area. So I did take away some of your points. It was very, very informative, very nice, actually, some new points. And for the audience, I would like to make a little personal comment here. I've never met Mr. Waleed Shahid. Am I allowed, Dr. Rabia, to make some personal
Yeah,
comments here
yeah,
for
sure.
the audience? For the audience,
Yes, sure.
because I missed his introduction. I don't know how he was introduced. Maybe he was just introduced as a assistant professor from the top university of Pakistan, mashallah. But because I joined 10 minutes late and I saw his icon picture,
Yes, sure.
so for the audience, especially my Arab audience here, I think this is the mother of Mr. Waleed, who happened to be the principal of a very prestigious army school in Pakistan. Is this correct, Mr. Waleed? Is she the one?
Well, she's the one, but she's not my mother. She was the
Oh,
principal, and
yes. Oh, you are her
I.
student. That's why
Yes,
I
I am a
said
student.
I missed your introduction. I thought that you have this picture as a mother. Well, she's
Yeah,
your what should I say, abstract mother, or the
yeah,
other mother, the
spiritual or
second
whatever.
mom.
Yeah,
And I just wanted to tell my Arab audience here that this lady is, or as Mr. Waleed is saying, he is keeping this picture as his icon because he might be the student at that time when this school was attacked in a terrorist attack, in a very brutal attack. And she took her students into the locked room, maybe in a bathroom or something, tried to save and face the terrorist, and she faced the open live fire, and she was killed on the spot. So,
yeah.
mashallah,
I'd like to add to that, if you allow me for a minute.
yes,
Her name is Miss Tahira Kazi, and she was the principal of the school. One of the most heinous terrorist attacks this world has ever
yes,
seen. And well, I did my matriculation from that particular school back in 2002, but the attack happened in 2014, probably. But as a as
but
a
you are still giving her
yes, a
a
gesture of
respect.
respect,
She is very
because
lucky lady.
she had a way out, but she gave her life for the students, and
Yes, yes.
that's we
That's why
should always appreciate.
I felt that it is important for me to add this personal comment here, although I was all the time in Saudi during those days when this thing happened to you. And mashallah, you have come a long way due to the teachers like this lady.
Indeed, indeed. Thank you very much, Miss Misma, for the comment and for adding up to the knowledge. As someone has pointed out about sharing the PDF in the slides, I'll share that with Mem Rabia as soon as this finishes, and she'll definitely share with you. My email is in the presentation as well, and you can always get back to me. And I would
Thank you
love to
so
hear from
much.
you.
Thank you so much, Ms. Waleed. Definitely, I will share the slides with all the participants. And thanks one again. And thank you so much for all to join.
Thank you, Zee.
Allah Hafiz.
Allah
Assalamu
Hafiz.
alaikum.